Hi, today we're going to be doing a brief overview of the transformation geometry that we have learnt, and we're going to be practicing with some different kinds of questions that we haven't done before. So we're going to start off by just reminding you that when we transform points or shapes on the Cartesian plane, then the image of point A after a transformation is called A prime. So if it's point B, then it'll be called B prime, and so on. The first kind of transformation that we learnt about was translations. Translations are where you are moving points or shapes around on the Cartesian plane. Horizontal translations are where you are moving from left to right or right to left. So you're moving in a horizontal direction like this. And when you are moving a point or a shape horizontally, the x values will increase or decrease. Our rule that we got for horizontal translations is if you have a point t, which is translated a unit to the right, then the x value is going to increase by a, because as you move to the right on your Cartesian plane, the x values increase. So x is going to go up by a. So it's going to be x plus a, and then the y value stays as it is. However, if point t is translated a unit to the left, then you're going in the opposite direction. That means that x is going to get less. So you're going to be subtracting from x. So it's going to be x minus a, and then the y stays the same. If you have vertical translations, that means that you're going up or down like this on the Cartesian plane. When you have vertical translations, then the y value is going to increase or decrease. And our rule is that if you have point t, which is being translated b units up, then the y value is going to increase, because as you go up on the Cartesian plane, the y values go up. So your y value will increase by b. So x is going to stay as it is, and you're going to have y plus b. However, if you go b units down with point t, which has coordinates x, y, then those coordinates are going to change to x and then y minus b, because as you go down the Cartesian plane, the y values decrease. Okay, so that's vertical and horizontal translations. Now these can also be combined. You can also have horizontal and vertical translations happening at the same time. And then the horizontal part of it, so the left or right movement, is going to affect your x value, and the up or down movement is going to affect your y value. Translation transformations produce congruent figures. This means that they will change the position of the figure, but its shape or size will not be affected. Okay, so that's translations. Now we're going to go on to reflections, which we learned next. Reflections are where you get a mirror image of the shape or the point on the Cartesian plane with a mirror line, which would be your x or your y axis. Okay, so the first one we did was reflections in the x-axis. That means that your mirror line is the x-axis over here. When you have a reflection in the x-axis, then the y value will change sign. So if you've got point t reflected in the x-axis, where t has the coordinates x, y, whatever those might be, then when you reflect it in the x-axis, the x value is going to stay as it is, but the y value is going to be multiplied by -1 to change its sign, giving you x negative y. Okay, so that's reflections in the x-axis. Then if you reflect in the y-axis, so our y-axis is over here, it's now our mirror line, then the x value is going to change sign. So if we look at our rule, then if point t is reflected in the y-axis, then if it has coordinates x, y, they will change that the x value changes sign and the y value stays the same. So you'll have negative x, y. Okay, just like for translations, reflection transformations produce congruent figures so that they will change the position of the figure but not its shape or size. Okay, then we had rotations. Rotations are where you're turning your point or your shape around on the Cartesian plane around a particular center of rotation. We only dealt with rotations where the center was the origin, and we only did 90-degree or 180-degree rotations as well. So here we've got a 90-degree rotation in a clockwise direction. So remember, with rotations, there are three parts to it. There's the angle, there is the direction, and there is the center of the rotation. So our center of rotation is always the origin. It will either be clockwise or anti-clockwise as the direction. Remember, clockwise is going around this way in the direction that a clock turns, or the hands on a clock turn, and anti-clockwise is the opposite direction. So in this case, we're looking at clockwise directions, and then your angle is how far. So a 90-degree angle is a quarter turn. Okay, so first of all, this example over here, if you've got a 90-degree clockwise rotation about the origin, then your x value will change sign and the x and y values will switch places. Okay, so let's have a look at what our rule looks like. If point T is rotated 90 degrees clockwise about the origin, then if it has coordinates x, y, the x value is going to change sign. So we're going to multiply that by -1. It'll become -x. And then they're also going to switch places. So you're going to end up with y -x for the image of T after the rotation. If you rotate 90 degrees anti-clockwise about the origin, then it's going the opposite direction like this. Okay, then your y value is the one that's going to change sign, and x and y are still going to switch places. Okay, so our rule for point T being rotated 90 degrees anti-clockwise about the origin is, once again, you have your T with the coordinates x and y. The y value is now going to change sign. So we're going to multiply that by -1, so it'll be -y, but they're also going to switch places, so it's going to become -yx, like that. Okay, then if you rotate 180 degrees about the origin, now remember, when you're rotating 180 degrees, you don't need to be given a direction, because no matter which direction you go, you're going to end up in the same position either way. Okay, so they don't need to give you a direction when you're going 180 degrees. For 180 degree rotation, the x and y values both change sign and they don't switch places. Okay, so our rule looks like this. If you've got point T, which is rotated 180 degrees about the origin, then x is going to be multiplied by -1, giving you -x, and y is also going to be multiplied by -1, giving you -y, because they both change sign. So you're going to have -x, -y. Rotation transformations, just like translation and reflection transformations, produce congruent figures, changing the position of the figure, but not its size or shape. Then we had enlargements and reductions. When you have an enlargement or reduction, then there are two parts to the enlargement or reduction transformation. There is the scale factor, and there is also the center of enlargement or reduction. Now, we are only doing enlargements or reductions where the center of the enlargement or reduction is the origin. When you enlarge or reduce a figure, then the coordinates of each point in the figure are going to be affected based on the scale factor. So the x value and the y value are both going to be multiplied by the scale factor. So if you've got point T, which is being enlarged or reduced by a factor of k, where the origin is the center of the enlargement or reduction, then T's coordinates are going to change from x, y to x multiplied by k and y also multiplied by k. Enlargement and reduction transformations produce similar figures because the shape is changing size. It's no longer congruent like translation and reflection and rotation transformations all gave us congruent figures. Enlargement and reduction transformations are going to produce similar figures. So they're going to have a different position and a different size, but the shape is still going to stay the same. So when we're looking at enlargement and reduction transformations, because they are producing similar figures, not congruent figures, it means that the area and perimeter are going to be affected. So to work out the perimeter, you take the perimeter of the original figure and you multiply it by the scale factor, whatever the scale factor is. So if they say it was enlarged by a factor of 2, then you're going to multiply the perimeter by 2. If it was reduced by a factor of 1/4, then you're going to multiply the perimeter by 1/4. Okay, then the area is a little bit more tricky. You're not going to just multiply by the scale factor. To work out the area, you're going to multiply by the scale factor squared. So if the scale factor is 2, then to work out the area of the enlarged shape, you're going to multiply by 2 squared, which is the same as multiplying by 4. If the area, or if the scale factor is 1/2, then you're going to work out the area of the reduced shape by multiplying by a scale factor of 1/2 squared, which would be 1/4. Okay, so just be aware when you're working out for perimeter with an enlarged or reduced shape, you multiply by the scale factor. But if you're working out the area, you multiply by the scale factor squared. Okay, now let's have a look at an example. Now in this example over here, you have been given a transformation that has been represented in the diagram, and we need to fully describe this transformation in words. Okay, now when you describe a transformation, you need to say what type of transformation it is, and you also need to give more details about the transformation depending on what type of transformation it is. In this particular example, the type of transformation, if you look at it, you can see that this shape and that shape are flipped over. They're not the same orientation as each other. Over here, the C is on the left, and here the C is on the right. Over here, the B is on the right, and the C is on the left of the shape. So it's not just a shape that has been moved, which means it's not a translation transformation. This is a transformation where it is reflected in the y-axis. So what you need to do is first say that it's a reflection. Okay, you can't just leave it as a reflection though. You need to give more information. You need to say what type of reflection is it. It is a reflection in the y-axis. So when you are asked to describe a transformation, you need to first identify what type of transformation it is. Is it a translation? Is it a reflection? Is it a rotation? Or is it an enlargement or reduction? Once you've identified the type of transformation, you then need to go and figure out what more specifically it is in that type of transformation. So if it's a reflection, is the reflection about the y-axis or the x-axis? If it's a rotation, what is the angle of rotation? What is the direction of the rotation? What is the center of the rotation? If it is a translation, how many units was it translated and in what directions was it translated? So you need to give all of that information when you're describing it in words. Okay, so now I'm going to give you a couple of examples that you're going to do for yourself. But remember, when you do it, you need to make sure that you give both the type of translation or transformation. You need to give both the type of transformation and you need to tell more information about it as well. Okay, so for the first one you're going to do over here, you have got this diagram showing you triangle ABC, and here you've got the image of triangle ABC after it has been transformed. You need to describe the transformation shown in this diagram fully in words. I'm going to give you 30 seconds to work on this example. Okay, so let's go through that. So first you should have realized that this is a rotation transformation. Okay, now because we only do rotation transformations with the center of the origin, we already know that that is going to be the center, but we do also need to know what the angle of the rotation is and what direction the rotation is. So in this case, it was going from here to there, so it's a 90-degree rotation. It's only a quarter turn rotation. If it was 180 degrees, it would have gone all the way into this quadrant over here. It's only a 90-degree rotation. So the rotation is of 90 degrees and the direction is anti-clockwise. Then you also have to say what the center of the rotation is. So it's about the origin. So that is what you should have got for this example. The next example is this one over here. You've got triangle DEF. And here you've got the image of DEF after it has been transformed. You need to describe this transformation fully in words. I'm going to give you 30 seconds for this one as well. Okay, so let's go through that. So you should have seen that this is a translation transformation. The shape hasn't been turned around or flipped over, it's just been moved. Okay, so it's a translation. Then you had to give more information. How was it translated? So if we look at the horizontal part of the translation, it was moved from here to there. That's in the left direction, okay? So it went 1, 2, 3, 4, 5 places. If you're looking at point D to point D prime over here, it went 5 places to the left. So the translation is 5 units left. And then point D went from here up 2 places to where D prime is over there. So the translation is 5 units left and 2 units up. Okay, next one. Here you've got triangle GHI, and here you've got the image of GHI after a transformation. You need to work out and describe this transformation fully in words. So I'm going to give you 1 minute to work on this one. Okay, so first of all, you should have seen that this is a reduction transformation because the shape got smaller. Okay, then you had to identify what the scale factor was. So if we look at the horizontal side over here, remember I told you in the previous lesson we were doing enlargements and reductions, when you're wanting to work out the scale factor, it's always easiest to look at a vertical or a horizontal side if you can. So if we look at the horizontal side over here, it has a length of 4 units, and this one has a length of 1 unit. So we take the reduced side divided by the original side. So it's 1 divided by 4, which is a quarter. So our reduction scale factor is a quarter. So it was reduced by a factor of a quarter, and the center of the reduction is the origin. Okay, so that is what you should have got for question C. And then question D, here you've got triangle JKL, and the image of JKL after a transformation. You need to describe this transformation fully in words. I'm going to give you 30 seconds for this example. Okay, so let's go through that quickly. So you should have seen that this is a reflection transformation. It's been reflected, and you need to also say what the line of reflection was, and that is the x-axis in this example. So it was reflected about the x-axis. Okay, now let's have a look at our next example. Triangle ABC with a perimeter of 12 meters and area of 6 meters squared is enlarged by a factor of 5 to form triangle A prime, B prime, C prime. So we've been told here that this is an enlargement transformation. We've been told what the factor is. There's no diagrams involved in this one. What they want us to do is they want us to work out what the perimeter of the image of ABC is after the transformation. They've told us what the perimeter of ABC was. We need to work out what the perimeter of the image of ABC is after the transformation. Okay, so first of all, we need to use what we know about what happens to the area and perimeter when we're working with enlargements and reductions. Okay, so to work out the perimeter, we're going to take the perimeter of the original shape. So first of all, the perimeter of A prime, B prime, C prime is equal to the perimeter of the original shape multiplied by the scale factor. So I'm going to multiply this by 5. So the original shape had a perimeter of 12, and we're multiplying it by 5 to get the perimeter of the image of ABC after it has been enlarged. Okay, and that should give you 60, and because it is given to us in meters, it's going to be 60 meters. Right, so that's question A, the perimeter. Now we're going to go on and work out the area of A prime, B prime, C prime. Okay, and that, in order to work that out, we need to now take the area of the original triangle and multiply it by not just the factor, so it's not just 5, we're going to multiply it by the factor squared. Remember, when we're working out the area of a shape that has been enlarged or reduced, we multiply the original area by the factor squared. So we multiply by 5 squared, which is the same as multiplying by 25. And that is going to give us 150. And then the unit of measurement is meters squared. So remember, when you're working out perimeter of a shape that has been enlarged or reduced, you multiply the perimeter by the factor. When you're working out the area of a shape that has been enlarged or reduced, you multiply the area of the original shape by the factor squared. Okay, so now I'm going to give you one to do on your own. So here you've got rectangle ABCD with a perimeter of 20 centimeters and an area of 24 centimeters squared. And it is being reduced by a factor of a half to form rectangle A prime, B prime, C prime, D prime. Now you need to work out the perimeter of the new rectangle and the area of the new rectangle as well. I'm going to give you 2 minutes to work on this example. Okay, so let's go through that quickly. So first of all, you had to work out the perimeter of the new rectangle. So the perimeter is equal to the original rectangle's perimeter, so it's 20, multiplied by the factor of a half. So it's 20 multiplied by a half. Now, half of 20 is 10. So you should have got 10 centimeters. That's our unit of measurement over there. So the perimeter of the image of ABCD after it has been reduced is 10 centimeters. Now let's work out the area. So to work out the area, you had to take the area of the original rectangle, which is 24, and you had to multiply it by the factor squared. So 24 multiplied by a half squared. Now when you work that out, it's the same as 24 multiplied by a quarter. Remember, when you are squaring a fraction, you square the top and the bottom. So it's 1 squared over 2 squared, so it's 1 over 4. And that gives you a quarter of 24, which is 6. So that should have been 6 centimeters squared. So that's what we should have got for that example. And that is how we work with translations, reflections, rotations, and enlargements in transformation geometry. Now that we've learned the concepts in this lesson, it's important to practice, practice, practice. If you haven't already got the worksheet that goes with this video, you can find it by clicking on the link in the description below. The worksheet comes with an extra exercise full of questions for you to work on to master the concepts covered in this lesson. If you found this video helpful, please hit the like button so that others can benefit from it too. Also, be sure to subscribe so that you can easily find my other lessons, and hit the bell so that you will get notified about lessons as I upload them.